Hi everyone, my name is Ben Levine and this is my project presentation. So the purpose of my capstone presentation is to create an FME workbench to help local government tax assessors orient street-level imagery toward building fronts. Building fronts are an important vantage point for assessors because it allows them to quickly determine property condition and classification. If properties can be quickly appraised with street-level imagery, especially for municipalities tasked with managing hundreds of thousands, in some cases millions of properties, an FME workbench and its outputs will promote efficiency and encourage tax assessors to continue to adopt technology. To start my presentation, I'm going to walk through some background as to why this project is important. Tax assessors in the United States are responsible for estimating property values for tax purposes. Assessors need to rely on technology to perform more site visits than they would on foot, which is the traditional way that they do it. This is particularly important because local offices are often understaffed, making it difficult to appropriately assess large quantities of properties. For tax assessors that have begun to adopt technology, it's traditionally been through aerial imagery. An example is shown here from Esri's imagery base map. Aerial imagery allows users to see full properties, including backyards, building footprints, and roadways. However, they don't show much detail about the front or sides of a property for their condition, which also includes the windows and doors. Over the past decade, street-level imagery has become a viable tool for assessors to leverage. While aerial imagery continues to be the industry standard, many assessors have turned to street-level imagery to help supplement the assessment of properties and to provide a clearer view of building fronts to ascertain grade and condition as outlined in the International Association of Assessing Officers, or IAAO, which is the primary nationwide organization of standards development. Most commercially available street-level panoramic imagery is captured with mid-size SUVs like the one pictured here, with imaging systems attached to the roof racks. Each image that is taken exists at a specific X, Y, and Z coordinate. And again, this is an example of one of the cars from a street-level imagery provider that I personally work for called Cyclomedia. However, one of the challenges with street-level imagery is the initial view that an assessor sees when searching for an address or a parcel identifier. The default view often takes a parcel centroid, opens the closest image, then points in the direction of that centroid. Unfortunately, this simplistic approach often leads to a side or a back view of a building, since the closest image to a parcel centroid can be in an alley or a side street. So in the example that I'm showing here in the screenshot, I searched by an address which happened to be a corner parcel, and you can see that the initial view is on the side because the geolocated point has its closest image on that side view. Ideally, the initial view is the front-facing view of a property for condition assessment and for screenshots on property cards. Property cards assessors use for protests lodged by members of the municipality. They usually provide an image of the building as part of that case. So while it may seem trivial simply moving around the corner to the proper spot, the time really adds up when you have to do this for thousands of properties. So with that background set, my project goals are as follows here. Local governments need to see the front view by default to ensure efficiency and limit the amount of time spent navigating to the front of a building. The goal of this project is to create a process that improves the initial view of a property when utilizing street-level imagery to promote efficiency and encourage assessors to continue to adopt technology. Through research and personal experience I will explain in the following slides, I've decided that Safe Software's FME platform is the most appropriate way to solve this challenge. And here are some of the findings from the research phase of this project. So the research has shown that tax assessors need to rely on technology to perform more property appraisals than could be accomplished on foot to assess jurisdictional properties. Again, this has traditionally been done with aerial imagery, which studies have found that aerial imagery allowed for 5% more properties to be assessed than through traditional methods, and that the values were judged to be 12% more accurate. Research and judicial rulings have supported the use of computer-aided mass appraisal, or CAMA systems, to effectively appraise property. Imagery of property is cited as a valuable data input for these CAMA systems designed to maintain property characteristics, and it's also in line with the guidelines set forth by professional organizations such as IAAO. Despite challenges from the public, tax courts have maintained that CAMA systems are legal to use when estimating a property's market value. Studies have also shown that GIS plays a major role in property valuation. Remote sensing, including street-level imagery, is a major contributor to property valuation because it provides data for informed valuation and forecasting. CAMA, GIS, and remote sensing can be integrated together to create an accurate tool that is geographically precise and can also reduce site inspections. There have also been conferences and organizations dedicated to GIS in tax assessment, such as the GIS Valtech conference that happens every year. On to some of the more technical research that was done for this project. But basically the research has shown that positional properties are the key to aligning panoramic street level imagery to specific assets. So an asset in this case would be the building. Yaw, pitch, and horizontal field of view are the three measures that can be used to position street level imagery toward building facades. This image here is an example of yaw, which determines the rotation of an image on a 360-degree plane. So in this case, directly north would be 0 or 360, directly east would be 90, directly south 180, directly west 270, and so on. So if you think about a point on a map, we are trying to orient the position and pointing of that camera based off of the yaw, which is shown here as that 360-degree circle. Here is an image from one of my sources that shows a panoramic image elongated over 360 degrees. The best way that I can explain pitch is it determines the upward tilt of an image. So looking at the taller building in this screenshot here, you would have an elevated pitch or a higher number for that. And then if we wanted to look at maybe the cobblestone streets at the street level, it would be a much lower pitch based off of that kind of singularity across the center of the image. The final parameter is horizontal field of view, which determines the zoom level of the camera. So in this case, the camera is zoomed out. You can actually see the blue triangle in the screenshot there. The angle of that triangle from the image location is very obtuse because it's zoomed out. And this is opposed to the same image here, but zoomed in. And notice that the triangle is now much more acute in its angle, and therefore it's a smaller horizontal field of view. A review of past studies has shown that Safe Software's FME platform is an effective tool for linking GIS processes together. Some of you may be familiar with Model Builder, which is a kind of a similar tool. But some of the key transformers within FME include attribute generation, value generation, and geometric processing. Furthermore, it can be used for assigning address information to buildings, which is a key part of the expected workflow during this capstone project. It's also compatible with GIS softwares like ArcGIS Pro to visualize and process data. In fact, FME is now the data interoperability tool within ArcGIS Pro. After all the research that I did identify that there is a gap in the research considering the position of street-level imagery specifically for tax assessors. Street-level images must have initial front-facing views of the property address to increase assessor efficiency, and the research has focused mostly on neural networks and semantic masks for building detection, but they have not explored using spatial relationships of assessor-maintained GIS data to predict the front-facing view of building facades. And realistically, most local government entities are not going to have the resources to go through the machine learning and AI tool set at this point. So this capstone project is looking to utilize the previous research of orienting panoramic imagery to appropriately create those initial views. It will also use the previous research of FME's ability to process GIS data to create efficient workbenches, and those workbenches consume local government GIS data. Together, these two factors will contribute to a scalable front-facing property view that can be input into CAMA systems and help make local government assessors more efficient. And now for the data that I expect to use as part of this project. The primary data set for this project is going to be a FileGeo database that includes GIS data from the Webb Central Appraisal District in Texas. The Appraisal District's GIS team manages the geospatial data, which consists of parcels, street center lines, and building footprints. Since assessors need to view buildings to complete their assessment, the geometry of the footprint will be used to focus the default view of that street-level imagery. The workbench will use the footprints to focus on the front-facing view to promote efficiency, but the parcels, as polygons, they provide the spatial location of each property unit. And what's most important about the parcels is that they include vital information like address, the unique parcel identifier, the appraised value, and the land use code. So the primary purpose of the parcels is to extract that attribution and attach it to the building footprints. Parcels share a spatial relationship with buildings. You can see in the screenshot here, the parcels are those pink boundaries and the building footprints are the blue boundaries. But by attaching that information, and of course it's going to be easy because they do share that spatial relationship, a spatial join should suffice. The unique identifier is how tax assessors search for property, so it really is the most important thing to extract from the parcel data set. The address information is important to compare to the street center lines when determining the likely front of a building. So the center lines provide two important functions. The first is that the street name attribute can be compared to the address information from the parcel to confirm the likely front-facing view of a property. The second function is that they'll be used to spatially select the street-level images that are near the front of that property. So for example, if a street name is Main Street and it matches the address of a building at 10 Main Street, all image locations that fall near the centerline Main Street will be considered as a possible option for a front-facing view. The next data set needed to complete this analysis is the location of the street-level images. That data set is provided as a CSV with information related to the location, date, and unique image identifier, just like the spreadsheet shown here in the screenshot. It is provided by a street-level imagery provider, in this case Cyclomedia, which does not publish it publicly, but as an employee I will have access and permission to use that data set to complete the analysis. Once they are converted, they will show up as geospatial points based off of that location, and they look just like points as you see on the screenshot there in the map. So they're basically separated by 5 meters throughout the street center lines where imagery has been captured. The final data set required for this project is the panoramic street level imagery captured by vehicles with high resolution cameras mounted to the roof. While the purpose of this project is not to deliver those images, the output of the workbench needs to be sufficiently tested to ensure that the results are accurate. So Cyclomedia provides a cloud-based image viewer called StreetSmart that can be used to test those outputs. The viewer consumes URLs that can specify unique image identifier, the yaw, the pitch, the horizontal field of view, basically all of the parameters that we're looking to ascertain for each individual building. So this is basically just going to be our testing platform. And now for the methodology that I intend to use as part of this project. So the first step is geospatial data preparation, and the first data set that needs to be prepared is the parcel data set. So parcels include, like I mentioned before, important attribution like address, unique identifier, appraised value, and land use code. The addresses in particular need to be investigated to determine if the street name is in its own column or part of a wider address field. In this case, the latter is true, so Amberjack Road would need to be isolated from the address number of 14. The second data set that needs to be prepared is the street level image locations, which are also shown on this map. And the primary process to prepare the image location data set is converting the CSV to a feature class using the XY table to point tool in ArcGIS Pro, which has already been done in this screenshot. The next step in the methodology is a spatial join. So since the assessors need to view buildings to complete their assessment, the geometry of the building footprints will be used to focus the default view of street level imagery. However, that parcel attribution is extremely important, specifically the street name like I just discussed. And so it's important for searching and comparing to the street name assigned to the image points. A spatial join will be performed to transition the parcel attribution to the building footprints. Then a spatial join will be performed between the local government center lines and the image points to assign a street name to each image point. At the conclusion of the two spatial joins, both image points and parcels will have a consistent value that can be compared to one another to determine the front-facing image candidates. So this is where the methodology gets a little bit more complex. So what we want to do is, with the qualified street level images identified for each parcel, a workbench needs to be run that finds the closest qualified candidate to the building footprint centroid. The closest image by distance is preferred to provide the most detailed view of the grade and condition of a building. A line will then be created between the 2 points to represent the initial view from image location to the building centroid. In this case, that's the green line in those images going from the image locations to the centroid of the building. Since panoramic images have 360-degree horizontal fields of view, the azimuth of the line is then calculated to determine the yaw. So in the case of the building on the left, looking at it, just eyeballing it, that's approximately 170, since 180 degrees would be directly south. If the building footprint attribution includes height, it will be used to calculate the pitch. So again, if we revisit pitch, taller buildings, we would need a higher pitch. If it was just a single story, 0 would probably suffice. To create the final image parameter, the horizontal field of view, the angle of a triangle created from the image location to a bounding box around the building footprint will be calculated. So residential building footprints are rarely perfect rectangles or squares due to porches and attached garages. So bounding boxes make for just a simpler way to create the base of a triangle for which the angle is calculated. So if we look at the screenshot again, you can see in blue basically the triangle that's created when we create the base of a triangle from the bounding box of the building and then connect that to the image location point. So again, together these image parameters combine to generate that front-facing view of a property that will be used in a URL. I wish that all buildings were similar to the last screenshot I showed, but that's just not the case. Parcel boundaries can be in many different shapes and sizes, some of which lead to buildings that are behind others, or areas where street-level imagery is just simply unavailable. These cases need to be identified and corrected using spatial relationships so that the final output does not show incorrect properties. So if a property cannot be viewed, it will be labeled as no image to prevent confusion amongst local government assessors. This shows a good example of a parcel that's set back with a longer driveway. So it's important to find not only the closest image location on the right street, but also the one that shows the correct property. So for example, if that initial vision line crossed over another building footprint or crossed over another parcel, there's definitely going to have to be a part of the process that corrects that to make sure that the recording point that has an unobstructed view to the building is chosen. So the final output will include an FME workbench that processes the local government data I just discussed, and then outputs a URL that contains the positional characteristics for each property. These URLs can be tested in a street-level viewing platform to confirm those front-facing views. With the initial views created for each property, assessors will be more efficient when appraising those individual buildings. I've discussed most of the software already, but there are 3 primary softwares that will be used for this project, and those include Esri's ArcGIS Pro, Safe Software's FME, which stands for Feature Manipulation Engine, and Cyclomedia's StreetSmart for the testing part of the process. ArcGIS Pro will be used to prepare the geospatial data and perform the spatial joins. FME will provide the robust catalog of transformers that can link spatial analysis into one process for easy investigation and troubleshooting, specifically for creating those initial views and the image parameters. And FME will be used for the parcel correction and ultimately the output of the final delivery. As mentioned before, StreetSmart will be used to test that final output, confirming front-facing views of properties based off of the image parameters output from FME. In conclusion, this capstone project will create an important workflow that will streamline technology use amongst local government tax assessors. The FME workbenches and subsequent property URLs will help assessors leverage their investment in imagery and allow for more properties to be appraised for fair market value. By creating a more accurate front-facing view of buildings, assessors will limit the amount of time spent navigating in street-level imagery to find the front of a building. This will lead to more appraisers in a shorter amount of time, just like aerial imagery has already assisted with. The GIS processes and logic used to create the workbenches will be comprehensive, considering both standard residential parcels and the edge cases where properties are difficult to view. And here are 2 slides with the references that I've used so far. I'm happy to provide those for anyone that is interested in some additional reading about orienting street-level imagery or GIS's impact on tax assessment. Thank you so much for listening to my capstone proposal. I'm really looking forward to the feedback from the peer review sessions and looking forward to learning from everybody else's project. Thanks again.